Welcome to another organic chemistry video lecture. We are still looking at functional group chemistry. Today's focus is benzene and the nucleophilic versus electrophilic reactions. Our essential understanding continues to be that organic molecules have structures and they go through reactions. Our objectives are, we're going to describe the structure of benzene, this super cool molecule, and then we're going to compare and contrast electrophilic and nucleophilic reactions. So first up, benzene. So benzene is a super cool molecule, C6H6. We know that it is aromatic, which means that it comes in this ring structure. It smells. So this German scientist Kekule said, I think that benzene looks like this. We've got our 6 carbons in the ring. Each carbon has a hydrogen. And then he thought it made sense there would be a double bond and then a single bond and then a double bond and then a single, double, single. So we had these alternating double, single carbon bonds. But then we learned some more and we built some new tools. We were able to understand bond lengths. So we know from investigations that a carbon-carbon single bond has a length of about 154 picometers, and a carbon-carbon double bond has a length of about 134 picometers, which means that benzene should have a bond of 154 picometers, and then a bond of 134 picometers, and then a bond of 154, etc., etc. But it turns out that all the bond lengths are just about 140 picometers long. So we don't have alternating single doubles. Instead, we have 140, which is kind of halfway between a single and a double. Perhaps it's like a 1.5 bond. So it turns out that we've got some resonance structure. Remember that resonance is when we've got these electrons, especially in double bonds, that can move around in more than one space. We call those delocalized electrons. These electrons are not stuck here between these two carbons, but instead can move around the whole entire molecule. So we have resonance, we have these bonds that are neither double nor single, but kind of halfway in between the two. And this makes benzene super, super stable, not a whole lot of reacting done by benzene. One of the few reactions that benzene will engage in is called electrophilic substitution. So electrophiles are positively charged and they're attracted to negative things, which makes sense because electro, like electrons, are negative, and then phile means love or attracted to or something like that, right? So they're positively charged things that are attracted to negatively charged things. So the negatively charged region that benzene has that might attract an electrophile are those delocalized electrons. We've got these delocalized electrons that are floating around in multiple spaces around the benzene molecule. You could have a positively charged particle like this Na2 plus guy that is going to be attracted to these delocalized electrons in benzene. In organic chemistry, we always draw arrows in the direction of electron movement. So these electrons are going to be attracted to that NO2 positive piece. What happens is this intermediary guy, this hydrogen was already here. We just don't always draw all the hydrogens, right? So this hydrogen was already here. What happens is this NO2 comes and sticks because it likes those electrons, those delocalized electrons. For a very short time, we have this super unstable thing where we've got a lot of stuff going on. But then these electrons that are here are going to get pulled back in. Again, notice the direction of the electron movement, get pulled back into that resonance space inside the benzene molecule. We're going to pull out that H and turn it into something else, probably a water molecule. And then this NO2 will be stuck here in this spot. We call it an electrophilic substitution because we substituted the NO2 for that H that I definitely scribbled all over. We substituted the NO2, replaced that H with the NO2, so that's why it's substitution. And then it's electrophilic because the NO2 was attracted to those delocalized electrons that are in the benzene molecule. So benzene will engage in electrophilic substitution. It will not engage in some of those reactions that alkenes do. So addition and polymerization. This is not a thing that benzene's going to do, even though it ends with an ene, and even though sometimes we draw it like it's got those double bonds like an alkene. It's not really a real alkene because it has that resonance structure. Not really double bonds, but more like 1.5-ish bonds. Good? Good. All right. So you can probably guess that if we've got electrophilic reactions, we've also got nucleophilic reactions. So we can also have nucleophilic substitution reactions. Nucleophilic, these are nucleus of an atom is positively charged. So things that love something that is positive is probably going to itself be negative. And that's exactly what we've got. So what happens in nucleophilic substitution, I've got this negatively charged hydroxide ion. It's a nucleophile because it's negatively charged. It's going to love things that are positively charged. Here in this molecule, I have chloromethane. Chloromethane. Remember that because of electronegativity differences, sometimes electrons are not shared equally. So even though we've got electrons being shared between carbon and chlorine here, chlorine is holding on to them more strongly. So the electrons are closer to the chlorine, further away from the carbon. That means that this chlorine is going to be partially negatively charged, which leaves the carbon to be partially positively charged. It's kind of like a nucleus in that it's positively charged. And this hydroxide ion comes along, it's negative, it sees this positive, and it's like, oh, I want to be your friend. So because carbon is partially positive because the chlorine is pulling the electrons away, hydroxide can come in here, bond to that carbon, and knock the chlorine off. So now I have this chloride ion by itself, and the hydroxide ion will substitute itself in for where the chloride was. And this is happening, again, because of electronegativity differences. The carbon is a little bit positively charged because that chloride was more electronegative than was the carbon. So this is a nucleophilic substitution reaction. We have a nucleophile in that carbon because of the electronegativity differences between carbon and chlorine. That hydroxide ion is going to come in and substitute itself for that chloride ion, nucleophilic substitution. All right, so here we have lots of reactions. Some are nucleophilic and some are electrophilic. I want you to guess which ones are which. Are we ready to get set? Let's look at this one first. So we have seen this reaction before. So this is ethene or ethylene. Both names are correct, ethene, ethylene. I've got this double bond. Double bonds mean I've got extra electrons. Extra electrons means that this is a little bit negatively charged. What's going to happen is an electrophilic, and this one is an addition reaction. So this is an electrophilic addition reaction. These hydrogens are attracted to all this extra negativeness from the electrons in that double bond. So electrophilic, because we are attracted, we love that electron region. So the hydrogens are attracted to that electron-rich region, which is a little bit negatively charged, hence the electrophilic part of it. It's an addition reaction because we're adding the hydrogens to the molecule where that double bond used to be. We're not substituting, we're just adding. Good? All right, let's look at this one. What do we think about this one? So be careful, this is not benzene. If it were benzene, we would have also these double bonds drawn in here, or we would have resonance drawn in here. We don't have that. We only have this one single bond, which means that this might actually be an addition reaction that can happen unlike in benzene. So I definitely do have this addition reaction, right? So we had hydrogens here and here, double bond here. What's going to happen is the bromine is going to add itself into those spaces. We're going to go from double bond to single bond. So it is an addition reaction. Is it electrophilic or is it nucleophilic? What do we think? That double bond means I've got an electron-rich region. This one is yet another electrophilic addition reaction. So again, addition, not substitution. All right, let's look at this one. Let's look at this one. You might be thinking, haha, I see double bonds. That means electron-rich regions must mean electrophilic. No, it's not. Here's the crazy thing. So I've got this carbon here and fluorine here. Fluorine is quite a bit more electronegative than that carbon is right there, which means that that carbon is left to be a little bit positive, right? This hydroxide ion is negatively charged. It is attracted to the positiveness. This guy is a nucleophile. So that hydroxide is going to be attracted to the partially positive carbon. It's going to knock that fluorine off and take its place. So this is nucleophilic because that hydroxide ion is attracted to that partially positive carbon. And because we are trading fluoride for hydroxide, it is going to be a substitution reaction. So this is nucleophilic because the hydroxide is negatively charged, attracted to the partially positive carbon. Substitution because we flipped out that fluoride for hydroxide. Okay, my friends, one more. I've got water, and then I've got this fluoroethane. You might be thinking, fluorine here, perhaps this is again nucleophilic. You'd be right. So again, we've got those electrons. Electrons are going to be more closely attracted to the fluorine. Fluorine will be partially negative. That leaves that carbon to be partially positive. If I heat up this reaction big, I need a lot of heat energy. We can get this water to split a little bit into hydrogen and hydroxide. That hydroxide is going to be negatively charged. It's going to be attracted to the partially positive carbon. So again, we've got this positive carbon, so this is going to be nucleophilic. It's going to be nucleophilic, and then that hydroxide is going to slide in there because it's attracted to that positive carbon. It is going to substitute itself for that fluoride. So we're going to knock the fluorine off. That hydroxide is going to take its place. I now have 2 carbons, meth-eth, and a hydroxyl group, which makes this an alcohol. We made ethanol. And then this H and the F that got knocked off are going to make hydrogen fluoride. So we have ethanol and hydrogen fluoride. This is nucleophilic, and it is substitution because we traded the hydroxyl group for that fluoride group. Good? All right. And we did it. Quick and easy. We talked about benzene. It is that lovely hexagon. Even though sometimes we draw it with those alternating single double bonds, in reality, it is a resonance structure with lots of delocalized electrons, which makes it super stable. And then we talked about electrophilic and nucleophilic reactions. Electrophiles are positively charged things that love things that are negative, like electrons. Nucleophilic reactions, now I have negative things that love things that are positive, like the nucleus of an atom. Good work today.